In this lecture, we review selected results from distribution theory that will be needed as we study structural equation modeling, SEM, and hierarchical linear modeling, HLM. Here's an outline of what we'll be looking at in this video. We'll first review the concept of and define the expectation of a function of one or more random variables. We'll then define the mean of a random variable and the variance of a random variable, which are defined in terms of expectation. We'll then define covariance and correlation of two random variables. Finally, we'll define stochastic independence of two or more random variables. So let's look at the expectation of a function of one or more random variables. Let x be a random variable with sample space, which we will denote by script A, and denote by lowercase f, the probability density function, or PDF, of x, if x is continuous, or the probability mass function, PMF, of x, if x is discrete. Let g be a function of x. Then g of x is a random variable itself. The expectation of the random variable g of x is denoted by e of g of x, where e is for expectation, and it's defined in the following way. If x is a continuous random variable, then the expected value of g of x is defined to be the integral over the real line of the product of g of x times f of x. If x is a discrete random variable, then the expected value of g of x is defined to be the sum over the entire sample space, script A, of g of x times f of x. In each case, the expected value is a weighted average of the values taken on by the function g of x, and the weight function is the function f of x, which again is the PDF of x if x is continuous, and the PMF of x if x is discrete. Next, let's define expectation in the context of two random variables. So let x1 and x2 be random variables with joint sample space, which we will again denote by script A, and denote by lowercase f the joint PDF of x1 and x2 if x1 and x2 are continuous, or the joint PMF of x1 and x2 if x1 and x2 are discrete. Let g be a function of x1 and x2. Then the function g of x1 and x2 is a random variable itself. The expectation of the random variable g of x1 and x2 is denoted by e of g of x1 and x2 and is defined in the following way. If x1 and x2 are continuous so that f represents their joint PDF, then the expected value of g of x1 and x2 is defined to be the double integral over the plane of g of x1 and x2 times f of x1 and x2. If x1 and x2 are discrete, then the expected value of the random variable g of x1 and x2 is defined to be the double summation over the entire joint sample space, script A, of the product g of x1 and x2 and f of x1 and x2. Now let's look at some properties of expectation. So let x be a random variable and let a and b be constants. Then the following equalities hold. The first equality says that the expected value of b is just equal to b. In words, this says that the expectation of a constant is equal to that same constant. The next equality says that the expected value of a times x plus b is equal to a times the expected value of x plus b. Now note that a times x plus b is a linear transformation of the random variable x, and it is itself a random variable. And so in words, this is saying that the expectation of a linear transformation of a random variable is equal to that same linear transformation applied to the expectation of the random variable x itself. Because of this, we say that expectation is a linear operation or a linear operator. Next, let x1, x2, and so forth up to x sub n be a collection of random variables, and let a1, a2, and so forth up to a sub n be a collection of constants. Note that the linear combination given by the sum I going from 1 to n of a sub I times x sub I is itself a random variable. The following equality involving the expectation of this random variable holds. Specifically, the expected value of this linear combination, that is, the expected value of the sum I going from 1 to n of a sub I times x sub I, is equal to the sum I going from 1 to n of the terms given by a sub I times the expected value of x sub I. In words, this says that the expectation of a linear combination of random variables is equal to that same linear combination applied to the expectation of those random variables. Now, this result is stated in terms of a finite number of random variables, but the result actually holds for a countably infinite number of random variables as well. Now that we've defined expectation, we're going to talk about several distributional characteristics that are defined in terms of expectation. The first characteristic is the mean of a random variable, or equivalently, the mean of the distribution of a random variable. Let x be a random variable with sample space denoted by script A, and denote by lowercase f the probability density function, or PDF, of x if x is continuous, or the probability mass function, PMF, of x if x is discrete. The mean of the random variable x, or in other words, the mean of its distribution, if it exists, is defined as the expected value of x. In other words, if x is a continuous random variable, then the expected value of x, which is the mean of the distribution of x, is given by the integral over the real line of x times f of x. If x is a discrete random variable, then the mean of the distribution of x, which is defined to be the expected value of x, would be the sum over the sample space script A of x times f of x. Again, this is provided that the integral or the sum exists and is finite. And if it is finite, if it exists and is finite, then that quantity is the mean of the distribution. Now note that the expected value of x, the mean of the distribution of x, is a weighted average of the values taken on by the random variable, and the weight function is the PDF if x is continuous, and the PMF if x is discrete. So again, the mean of a random variable, or equivalently, the mean of its distribution, is equal to the weighted average of the values taken on by that random variable. The next characteristic of a distribution is the variance. So again, let x be a random variable with sample space script A, and denote by lowercase f the PDF of x if x is continuous, or its PMF if x is discrete. Then the variance of the random variable x, or equivalently, the variance of the distribution of x, if it exists, is defined to be the expected value of the function g of x equal to the square of the difference between the random variable x and its expected value. That is, if x is a continuous random variable, then the variance of x is defined to be the integral over the real line of the product of the square of the difference between the random variable and its expected value with the PDF. If x is a discrete random variable, then the variance of x is defined to be the sum over the sample space script A of the square of the difference between the random variable and its expected value or mean with the PMF. And again, this is provided that the integral or sum exists and is finite. Next, we're going to look at the covariance of two random variables. Let the random variables x1 and x2 be jointly distributed according to some distribution. The covariance of x1 and x2, which is denoted in the following way, cov of x1 and x2, is defined in terms of expectation in the following way. The covariance of x1 and x2 is defined to be the expected value or the expectation of the following product: x1 minus the expected value of x1 times the difference x2 minus the expected value of x2. So this is the defining formula, the defining expression for the covariance of two random variables x1 and x2. The covariance of x1 and x2 can also be calculated using the following formula, which is easier to compute in many situations. In particular, the covariance of x1 and x2 is equal to the difference between the expected value of the product of x1 and x2 and the product of the expected value of x1 with the expected value of x2. Now, this formula is equivalent to the definition formula, and it can be derived using properties of expectation that we have already presented. It would be a good idea for you to make sure that you can derive this formula. So we have defined covariance, and we've seen an additional formula that we can use to calculate covariance. Now let's look at some properties of covariance. So property 1, which we can describe as the covariance of a random variable and a constant, is as follows. Let x be a random variable and let a be a constant. Then the covariance of the random variable x and the constant a is equal to 0. Now this is going to be true for any random variable x and any constant a. And so what this is saying in words is that the covariance of a random variable and a constant will always be equal to 0. Property 2, which basically says that the order of variables in the covariance function is irrelevant, says the following. Let x1 and x2 be random variables. Then the covariance of x1 and x2 is equal to the covariance of x2 and x1. So in other words, the covariance function is symmetric in its arguments. Next we have property 3. Let x be a random variable. Then the covariance of x with itself is equal to the variance of x. In words, this says that the variance of a random variable is equal to the covariance of the random variable with itself. Now this may seem kind of odd, and it may not be clear how we might use this, but it actually turns out to be very useful, and we can use this result in proving some of our subsequent properties. Next, let's look at property 4. this gives us information on the covariance of two linear combinations of random variables. Let x1 and x2 and y1 and y2 be random variables, and let a1 and a2 and b1 and b2 be constants. Then the linear combinations given by w equal to a1 times x1 plus a2 times x2, and u given by b1 times y1 plus b2 times y2. These linear combinations, w and u, are themselves random variables, and their covariance, the covariance of w with u, is given by the following decomposition. The covariance of w and u, which is the covariance of the linear combination a1 times x1 plus a2 times x2 with the linear combination b1 times y1 plus b2 times y2, is equal to a1 times b1 times the covariance of x1 with y1 plus a1 times b2 times the covariance of x1 and y2 plus a2 times b1 times the covariance of x2 and y1 plus a2 times b2 times the covariance of x2 and y2. Now, this decomposition is expressed in terms of linear combinations of two random variables apiece, but it can be extended to linear combinations of any number of random variables. Property 5 shows us how to calculate the variance of a linear combination of random variables. Let x1 and x2 be random variables, and let a1 and a2 be constants. Then the linear combination w, given by a1 times x1 plus a2 times x2, is itself a random variable because it's a function of random variables, and its variance is given by the following expression. The variance of w is equal to the variance of a1 times x1 plus a2 times x2, the variance of that linear combination, and that is equal to a1 squared times the variance of x1 plus a2 squared times the variance of x2 plus 2 times a1 times a2 times the covariance of x1 and x2. So this variance of a linear combination of two random variables x1 and x2 is expressed or can be decomposed into components that involve the individual variances and the covariance between the two random variables. Now, this result is given for two random variables involved in the linear combination, but it can be extended with a little bit of work to linear combinations of more than two random variables. In fact, any number of random variables can be involved. Property 6 gives us a way to calculate the variance of a linear combination of random variables that are pairwise, that have zero covariance among themselves. So let x1, x2, and so forth up to x sub n be a collection of random variables such that the covariance of x sub I and x sub j is equal to 0 for all I not equal to j, and let a1, a2, and so forth up to a sub n be constants. Then the linear combination w, given by the sum I going from 1 to n of a sub I times x sub I, is itself a random variable, and its variance is given by the following expression. The variance of w, which is the variance of the sum I going from 1 to n of a sub I times x sub I, is equal to the sum I going from 1 to n of the terms a sub I squared times the variance of x sub I. So the variance of this linear combination of random variables that have zero covariance among themselves is expressed in terms of the individual variances of the random variables. Now that we've defined covariance and variance, we can now define correlation. Let the random variables x1 and x2 be jointly distributed according to some distribution. The correlation of x1 and x2, which is denoted as core of x1 and x2, is defined in the following way. The correlation of x1 and x2 is equal to the covariance of x1 and x2 divided by the square root of the product of the variances of x1 and x2. Now, since the square root of the variance of a random variable is equal to the standard deviation of that random variable, we can also define and calculate the correlation of the random variables x1 and x2 as the covariance of x1 and x2 divided by the product of their standard deviations. So divided by the standard deviation of x1 times the standard deviation of x2. So that is how correlation is defined. Now let's look at how to interpret correlation. So what does the correlation give us? What kind of information is it providing? Correlation is a measure of the strength of the linear relationship between two variables. Correlation is always between -1 and +1. This is a mathematical certainty. It can be proven mathematically. Now, the sign of the correlation provides information about the type or nature of the linear relationship. The magnitude of the correlation provides information about the strength of the correlation, the strength of that linear relationship. A positive correlation indicates that a positive linear relationship exists between the variables. In other words, as the explanatory variable increases, the response variable tends to decrease. As the explanatory variable decreases, the response variable tends to decrease. On the other hand, a negative correlation indicates that a negative linear relationship exists between the variables. As one variable increases, the other variable tends to decrease. And as one variable decreases, the other variable tends to increase. Now, the closer the correlation is to -1 or +1, the stronger the linear relationship. On the other hand, the closer the correlation is to 0, the weaker the linear relationship. A correlation of 0 indicates that no linear relationship exists between the variables. Now, note, and this is important, a correlation of 0 does not indicate that no relationship at all exists between the variables. It only is telling us that no linear relationship exists between the variables. And then finally, a correlation of -1 or +1 indicates that a deterministic, a non-random linear relationship exists between the variables. So let's look at a few examples. So recall that the closer the correlation is to either -1 or +1, that indicates a stronger linear relationship. And so here we have a scatter plot of two variables, y and x, y on the vertical axis, x on the horizontal axis. And the correlation here is equal to 0.9928, which is very close to 1. Now we can see from the scatter plot that we have, number one, a positive linear relationship. As x increases, y tends to increase as well. We can also see that we have a very strong linear relationship. If we were to fit a line through that data set, in fact, I've done that here, we can see that there's not a whole lot of variation in the vertical direction from that line. And so this scatter plot is showing visually that we do have a strong positive linear relationship. And this is what we could discern without even seeing the graph if we, by knowing that the correlation is equal to positive 0.9928. Here's another example. Here we have a scatter plot showing a negative linear relationship between the two variables x and y. In particular, as x increases, y tends to decrease. If we fit a straight line to the data, we see that again, the data cluster very closely to that line. There's not a lot of variation or deviation from the line in the data points. And this tells us that not only is there a decreasing linear relationship, but it's a strong decreasing linear relationship. And we can see here that the correlation is negative 0.993. And so the value, the sign of the correlation tells us that there's a negative relationship, negative linear relationship between the two variables. And the fact that it's very close to -1 tells us that it is a strong linear relationship. All right, here we have an example where the correlation is 0.5872. So if we look at the scatter plot, there would appear to be an increasing trend, an increasing relationship between x and y, and that relationship looks like it may be somewhat linear. And so we would expect, based on that, for the correlation to be positive, which it is. But because the points do not fall consistently close to the line, there's a lot of variation or deviation in the vertical direction from the line, then the correlation or the strength of that linear relationship is not as strong as it was in the previous examples. All right, and that is indicated by the correlation of 0.5872. And so we see here that the weaker the linear relationship, the more variability there is in the vertical direction about the underlying line, and the value of the correlation is going to be attenuated. It's going to get closer to zero. In the previous examples, the absolute value of the correlation was around 0.99, but here it's 0.59. Here we have an example where there appears to be a decreasing linear trend between x and y. As x increases, y tends to decrease. When we superimpose a line through that data set, we see that there is a fair amount of variation or deviation in the vertical direction from that line. And so again, the strength of this linear relationship is not as strong as it was in the first two examples. In fact, this is more comparable to the strength of the linear relationship in the previous example. The difference being that in this example, we have a negative linear relationship as opposed to a positive linear relationship. So again, we see that the more variability there is in the vertical direction around the line of best fit, the weaker the strength of the linear relationship. And so the correlation is going to be further away from -1 or +1. It's going to be closer to zero. In this case, the correlation is -0.69. Here we have an example, and when we look at the scatter plot, it may be difficult to discern visually whether a line of best fit would have a positive slope or a negative slope. Now, when we go ahead and do an analysis of this data, we find that the correlation is actually negative, slightly negative, but it's very close to zero, -0.072. All right, and we can superimpose the line of best fit over the data set. And so we see here that that the line of best fit does have a negative slope, but that slope is very close to being zero, and that corresponds to the correlation being close to zero. And we can also see that there is a lot more variability in the vertical direction with this data set than for any of the other previous examples. And in fact, if you look at the vertical axis, you can see that the range of values is much larger for this data set than it was for any of the other data sets. And so because of the amount of variability in the vertical direction around that line of best fit, the strength of the linear relationship is very, very weak, and that corresponds to a correlation that is very close to zero. Now again, a correlation of either -1 or +1 indicates a perfect linear relationship exists between the variables. In this example, we have a data set where the points appear to be on a straight line. And if we superimpose a line of best fit, we see that the points all fall perfectly on that line. And so because there's no deviation in the vertical direction of the points from that line, we have a completely deterministic relationship between the two variables x and y. And corresponding to that, we have a correlation of +1. It's positive because this this linear relationship is positive, and it's 1 because it is a completely deterministic relationship. Similarly, we have here an example where the points fall perfectly on a line that has a negative slope. And so because of this, because of the negative slope, the correlation is negative, and because the points all fall perfectly on that line, the correlation is -1. We have a perfectly deterministic linear relationship between the two variables. Next, we're going to look at and define stochastic independence of two or more random variables. Let the random variables x1, x2, and so forth up to x sub n be jointly distributed according to a distribution with joint probability density function given by lowercase f, and with marginal PDFs f1, f2, and so forth up to f sub n respectively. The random variables x1, x2, and so forth up to x sub n are said to be stochastically independent if and only if the joint PDF, lowercase f, can be written as the product of the marginal PDFs f1, f2, and so forth up to x or f sub n. That is, x1, x2, and up to x sub n are stochastically independent if and only if the equality given by f of x1, x2, and so forth up to x sub n is equal to f of 1 evaluated at x1 times f2 evaluated at x2 times and so forth up to times f of n sub x sub n, if that equality holds for all x1, x2, and so forth up to x sub n. So this is the definition of stochastic independence of n random variables. Now, determining whether the random variables x1, x2, and so forth up to x sub n are stochastically independent using the definition requires that one know the joint PDF of the random variables as well as their individual marginal PDFs. Now, we may not have that information, or it may be difficult to obtain. The following result is similar to the definition, but the good thing is the advantage of this result is that it does not require knowing or finding the marginal distributions of the individual random variables first, and is therefore easier to use for the purpose of determining whether the random variables are independent. Now, for simplicity, the following theorems that I'm going to be presenting are stated for two random variables, but they generalize to n random variables in the obvious ways. So this first result, we'll call it theorem 1.1. Let the random variables x1 and x2 be jointly distributed according to a distribution with joint probability density function given by lowercase f. Then x1 and x2 are stochastically independent if and only if the joint PDF, lowercase f, can be written as the product of a non-negative function of x1 alone and a non-negative function of x2 alone. That is, the random variables x1 and x2 are stochastically independent if and only if the joint PDF f of x1 and x2 is equal to the product g of x1 times h of x2, where g of x1 is greater than or equal to 0 for all x1, and it's a function of x1 alone, and h of x2, which is a function of x2 alone, is always non-negative. Now, this result looks a lot like the definition, but here's the thing. The functions g and h are not necessarily the marginal PDFs of x1 and x2. These are any functions of x1 and x2 alone, as long as they are non-negative, as long as g is a function of x1 alone, and h is a function of x2 alone. And so what this allows us to do is it converts the task of trying to determine whether two random variables are stochastically independent from having to find the marginal PDFs into a factorization problem, and this is much, much easier to do. So if we can factor the joint PDF into two functions, into two components, g of x1 and h of x2, where g is a function of x1 alone and h is a function of x2 alone, and g and h are both non-negative, then we can conclude that the two random variables x1 and x2 are stochastically independent. So factoring like this is much, much easier than having to go through the calculations to find the marginal PDFs from the joint PDF and then multiplying those two marginal PDFs and checking to see if that's equal to the joint PDF for all values of x1 and x2. Next, we have what we'll call theorem 1.2. Let x1 and x2 be stochastically independent random variables. So we are assuming here that x1 and x2 are in fact stochastically independent. And so the result applies whenever we have two independent random variables. Now, let g1 be a function of x1 alone and g2 be a function of x2 alone. Then the expectation of the product of these two functions, that is the expected value of g1 times g2, is equal to the product of their expectations. That is, it's equal to the expected value of g1 times the expected value of g2. So again, if x1 and x2 are random variables, then these functions g1 of x1 and g2 of x2 are random variables themselves. Their product, g1 of x1 times g2 of x2, is another random variable, and the expected value of that random variable, the expected value of g1 of x1 times g2 of x2, is equal to the product of the expected value of g1 times the expected value of g2. Now, a word of warning here. If x1 and x2 are not stochastically independent, then this equality will not hold. All right? If they're not independent, then it will not be the case in general that the expected value of the product of g1 with g2 is equal to the product of the expected value of g1 and the expected value of g2. So we do not use this formula unless we know that x1 and x2 are stochastically independent. Now, a corollary to theorem 1.2 we'll call corollary 1.2.1, and this result says, let x1 and x2 be stochastically independent random variables, then the expected value of the product of x1 and x2 is equal to the product of their individual expectations. That is, the expected value of x1 times x2 is equal to the expected value of x1 times the expected value of x2. Now again, this is true when x1 and x2 are stochastically independent. If they're not independent, we cannot use this formula because it will not be true in general. Now, the proof of this result, this corollary, follows very easily from theorem 1.2 that we just looked at by setting g1 equal to x1 and g2 equal to x2. So try that and make sure you can derive this formula. Now, the next theorem is theorem 1.3, and this is a very important theorem. It says, let x1 and x2 be stochastically independent random variables. So when that's the case, when x1 and x2 are stochastically independent, the covariance of x1 and x2 is equal to 0. And that implies, as long as the variances are non-zero, that the correlation of x1 and x2 is also 0. So again, when x1 and x2 are stochastically independent, then they are uncorrelated as well. Now I have a question for you. is the converse of theorem 1.3 true? Well, let's make sure we understand what the converse of theorem 1.3 would say. The converse of theorem 1.3 would say the following. Let x1 and x2 be random variables such that they have a covariance of 0 and therefore a correlation of 0. So in other words, let x1 and x2 be uncorrelated random variables, or random variables with 0 correlation. Then x1 and x2 are stochastically independent random variables. So that statement, that whole statement, is the converse of theorem 1.3. And my question to you is this statement, is the converse of theorem 1.3 true? Think about that. So that's all I wanted to talk about in this lecture video. I'll see you in the next lecture video.